Okay, so today we're going to discuss one of my favorite topics, which is vorticity. So let's start with a few mathematical definitions, and then I'll give you a few physical pictures and show you how the concept of vorticity can be useful. So first of all, mathematically, vorticity is simply defined as a vector, and it's the curl of the velocity field. Now, we probably showed you earlier in when we discussed kinematics that vorticity, or the curl of the velocity, is really a measure of solid body rotation. So it tells us if the fluid is spinning or not. Just to remind you how to take the curl of a vector. Everybody seems to have their own rule for remembering how to take a cross product, but basically we're going to take the cross product of the gradient vector and the velocity vector, which has components u, v, and w, and the x, y, and z direction. So the way I always remember this is to write up the little matrix, and then you sort of cover up that row and take that cross, then that cross, and then that cross, and those are the three components. So the resulting vector is nothing more than and so that's the resulting vector. Now you might also remember some of your vector calculus identities, that if I take the divergence of the vorticity, that by definition, if I carry this operation out, the divergence of the curl of something, I always get 0. So vorticity is divergence free. And another definition we'll use a lot is the circulation. And the circulation will be defined as if we take a loop in our fluid, some sort of arbitrary loop, and we usually talk about that loop having normal vectors along the surface, but it also has tangent vectors everywhere. And if I take the integral around the loop of the velocity field dotted with the tangent vector and integrate along the length of the loop, that's what we'll call the circulation. And in vector calculus, there's another theorem. I won't prove it right now, but maybe we'll do it later, is that if I take the curl, the velocity, dotted with the normal vector, in this case, this would be a surface integral or an area integral over the region enclosed by our loop. So if I take this same loop, this is my loop L, going around this, I loop all the way around, but that bounds this whole surface. And so we have a theorem in vector calculus that tells me if I take the curl of the velocity dotted with the normal vector of that surface, so in this page, if we're in 2D, it points out of the surface all around that patch enclosed by the area, that those two things are equal. And just by definition, the curl of the velocity is the vorticity. So this is our definition of the circulation. We can then take the velocity field and integrate how it looks like the tangent vector all the way around. So you can see if the velocity and the tangent are aligned, it means we're going to have some sort of swirl around here. So we'd have a positive circulation. If the velocity field were pointing opposite, and we did our integral around, we get the negative circulation. And if we had regions of plus and minus and they exactly canceled, we get 0. And by definition of vector calculus, this value of the circulation we get from integrating around this loop must also equal the integral of the vorticity over this area. So those are just a few definitions. So let's look at the vorticity equation, and we're going to take a simplifying limit. We're going to take the limit where the viscosity is 0, the density is constant, and so therefore we're just really working with Euler's equations. So let's write out Euler's equations for this case, which is something that we have mass times acceleration equals the forces, which is the gradient of the pressure, and gravity. Now, since our density is constant and gravity is just a constant pointing in one direction, I'm going to rewrite this as the gradient of the pressure plus the hydrostatic piece. So we've done this before. So to get the vorticity equation, we simply need to take the curl of the entire equation. Now you might remember from vector calculus that if I take the curl of the gradient of anything, I get 0. So when I take the curl of this entire equation, the whole right-hand side is going to disappear. So in order to get our vorticity equation, I just have to know how to distribute the curl operator among this kind of funny operator here, v dot gradient v. Now I won't go through the details, I'll just sort of write the result. The final result would be that the material derivative of the vorticity is equal to the vorticity dotted with the gradient of the velocity. So we'll talk about what this equation means, but let's start with a very simplifying a limit. Let's start with another simplification, which is we're only interested in 2D flows. So we're going to have flow in a sort of the plane of the paper, so therefore our velocity vector will just be u, v, and 0, so there's no flow into the page, just flow in the plane. And our vorticity vector then, if we look back at what we had for the vorticity, we would find that those components are 0, the x and y components are 0, and so we only have z component of vorticity, meaning it's pointing or telling us the rotation around a point, around its axis pointing in the z direction. And that value is the partial of v with respect to x minus the partial of u with respect to y. And so what that means is, since we have velocity in the xy and vorticity in the z, when I take vorticity dotted with the gradient of velocity, I'll get 0. So in 2D, our equation will simplify to being the material derivative of the vorticity is equal to 0. So what that means is that basically the vorticity is sort of like a property that the fluid has. A little fluid particle starts off, it has some vorticity, it has some swirl, it's spinning around and around and around this point, whichever way it's spinning, and that vorticity just sort of moves with the fluid. So whatever vorticity it has here, later that little fluid particle is over here and has that same amount of vorticity. So vorticity moves with the fluid. Another useful thing that we can get in 2D is we can look at the circulation. Remember, the circulation was just defined as the vorticity integrated over some patch. So here's our little patch here, and since if we calculate the circulation then around a loop which moves with the fluid, so around a material loop, right, we'd be enclosing the same fluid for all time, and since the vorticity of a fluid particle or a piece of fluid has the same vorticity, it doesn't change because its material derivative is 0. What that would tell us is something that in a more general sense is called Kelvin circulation theorem, which would tell us the material derivative of the circulation around a closed material loop is 0. So this is a property that we'll use quite a bit. So let's talk a little bit about how we might see vorticity in a fluid flow. So let's start with a simple case here. Let's have kind of like an open channel like a river, and fluid is flowing down this river. And here you are standing on the banks of the river. So if we measured the velocity profile in this river, we know that the velocity needs to go 0 at the walls. And maybe this is an open channel, so it doesn't necessarily have to follow on the surface the parabolic velocity profile of the channel, but it does have to go to 0 at the walls. So the velocity profile might look something like that. Now let's imagine that we throw in this fluid a little floaty thing, and the little floaty thing is a cross. And actually, let me distinguish the axis here. So let me use a red and a black line. Okay, cool. So this point is going to move down and sort of go with the flow. It's going to move in this direction along the wall. But you can see that the velocity on the top side of the cross is lower than on the bottom side. So as it moves, it's also going to rotate. And so this little float with a cross on it, you could think of as being a vorticity meter. So if I throw this in the fluid and I see it spinning very fast, it means there's lots of vorticity. If I see it moving slowly, so sort of spinning more slowly, it means there's less. So this little cross is giving us the solid body rotation, or a measure of the vorticity. Now normally when we look at a flow, if we look at its streamlines, if we see things that are circular, we might be tempted to think there's lots of vorticity or lots of swirl, but that's not always the case. So one case, for example, where you find curved streamlines is when you look at the waves of water on the surface. So if here's the ocean, and here's the air, and here are some waves which are sort of propagating by. If we put little tracers in the fluid, we would find that those tracers, as a wave goes by, trace out a circular streamline. So a little particle here would trace out a path that would look roughly circular as this wave propagates by. So you might be tempted to think that this flow has vorticity, but you would be wrong. Because it turns out in this case that if we mark the orientation of the fluid particle, so here I'll draw it as a little face, the particle does move in a circle, but it wouldn't change its orientation. So this is kind of like a Ferris wheel. So the particle does move in a circle, but it always has the same orientation, so the particle's not rotating. So in this case, the vorticity is 0. Now, in another instance, we might have something like the following. So let's imagine we have a channel, sort of a step in it, and flow going this way. We've seen in previous examples that this flow has a lot of recirculation. So there's sort of some swirl or some streamlines that might look like closed circles swirling around here, right around the bottom part of this step. Now, in this case, if we looked at our little happy face, our little fluid particle, we would see that the orientation of the face changes as the particle swirls around. So in this case, we see circular streamlines, but the particle is actually rotating because this guy's orientation is changing. So this is more like a merry-go-round, where the vorticity is not equal to 0 because the fluid particle, our little happy face, is experiencing solid body rotation in this case, but not in this case. So now let's do a few qualitative examples. So we had our Kelvin's theorem, which tells us that if we take the circulation around a material loop, that the derivative of that doesn't change with time. So let's imagine that we have a fluid at rest. So at t equals to 0, we have a fluid at rest. And in the fluid, I've put my spoon. So this is just a cross-section of the back of my spoon, sort of dipped in the fluid. Now let's draw a material loop. And so this is the boundary which we're going to calculate the circulation, which is equal to 0 because the fluid is at rest. So there is no circulation. Now, right after time is equal to 0, I'm going to give my spoon a little flick. So I'm going to drag it through the fluid sort of spontaneously and just pull it. And when you do that, what you'll notice is that we have two vortices which shed off the back. So you can do this just in the cafeteria. You can take a cup of coffee, and take a spoon, and basically do this experiment. Sprinkle something on the surface to see it, or if you do it while you pour, like maybe say a little milk in it where it's not fully mixed, you'll be able to see the vortices. So you'll see one rotating clockwise and another one rotating counterclockwise. So they're spinning like that. And so what Kelvin's theorem tells you is that at time equals to 0, the circulation was equal to 0. Now I've sort of induced some flow. I've created these little vortices. But if I take this loop all the way out here, kind of far away from the spoon, that it still has to be true that the circulation is equal to 0. So the strength of the red vortex then has to equal the black one. So the total strength of the red has to equal the blue. So these are equal sized vortices of opposite signs, so that when I take the circulation, they basically cancel each other out. So it tells me these two vortices have to be of equal and opposite sign that I've created, because initially there was no vorticity, or I mean there was no circulation around my loop. So another example of just using vorticity to give us some qualitative information in Kelvin's theorem is when we talk about lift on an airfoil. So here's our little airfoil. Has a shape in 2D that looks something like that, and it's inclined at the flow. And if we simply measured the streamlines, we might see something like this. So this would be sort of the pattern that we observe. We see streamlines that look like this, and we'd see at the back that there's sort of this thin wake that, unless we're in sort of too high of an angle of attack where we're sort of in some sort of stall configuration, we'd see sort of a thin wake sort of separating from the airfoil right from the sort of trailing edge. But otherwise the flow would look smooth, and since an airfoil is usually at high speed, it seems like in this situation the Euler's equation should be okay, right? Because it seems like viscosity shouldn't play much of a role, because this would typically be a very high Reynolds number flow. So if we then took our airfoil shape and we solved Euler's equations, this is what we would calculate. So if we just solved Euler's equations for our airfoil shape, inclined at an angle of attack, what we would see is that at the back, the streamlines would actually leave the body or separate from the body at some point that wasn't consistent with the trailing edge. It might be a point, something like that. So the flow would actually wrap around that. So what we observe is actually consistent with the solution of Euler's equation, but with some sort of circulation sort of superimposed on that as well, right? Because if we take these streamlines and we add some circulation, we can essentially push that point down so that streamline leaves at the trailing edge. Now, this idea that we can take Euler's equation and kind of add an arbitrary amount of circulation until we move the streamline right to the trailing edge, right? There's no real strong theoretical reason for that, but it's what we observe to be about true. So there's some sort of circulation in this flow which is pulling these streamlines that Euler's equation would predict to push them down right to the trailing edge. So where does this sort of circulation, which appears to be in the flow, coming from? Well, let's go back to our sort of starting condition. So here's our airfoil, our airplane's on the runway. At time equals to 0, the fluid is at rest, and the airfoil is at rest. So let's take a big loop around here where we'll calculate our circulation, and it has to be 0 because everything is at rest. Now, at time equals to 0, I'm going to start moving my airfoil. So I'm going to take off. My airfoil is going to start moving in this direction. And what I would observe is that when I suddenly accelerate my airfoil, I have a little starting vortex which is shed from the airfoil. So now you can imagine that the circulation around this loop is equal to 0. So if I cut my region in half, the circulation around this loop, B, plus the circulation around this loop, A, must sum to 0 because it has to sum to the circulation around the total loop. So we can see in this region where I've got the starting vortex, it's spinning in this direction, the circulation is not 0. So what that means is that I need to have circulation in this region, which is in fact the circulation that we get around the airfoil that gives us the observed streamlines. So we have this kind of what we can call sort of a bound vortex, which is kind of maybe imaginary, but it's a true circulation around the airfoil, which is balanced by the starting vortex. So that's where the circulation can come from. So now let's see sort of qualitatively what a consequence of the fact that the material derivative of the vorticity is equal to 0 in 2D, or saying that vortices just sort of go with the flow. So let's imagine a situation where I've started off with two pairs. So the vortices are going to be equal strength. So we have a red counterclockwise vortex and a blue clockwise vortex. So these have equal strength. This guy here is just swirling around, so it's setting up a velocity field which is swirling around this point. And what that's going to do is it's going to push on this guy just a little bit. So it's going to impose a little translational velocity on our blue vortex. The blue vortex swirling in this direction is going to push on that vortex. And since these vortices are equal in strength and size, they're just going to push on each other equally, which means they're going to move in a straight line. Now you can do this experiment in the cafeteria again with just a cup in your spoon, so you can give a little flick and you can create these vortices, and you'll see they then translate and push each other and start running across your cup or your bowl. Now in your cup, you're going to have a wall, right, because it's not an infinite thing. And we can actually use this kind of idea of imposing the velocity field of one vortex on another to figure out what happens at a wall. So the way we figure this out is, since we're in an ideal fluid, the wall ends up being just sort of a reflection point or a point of symmetry. So if we want to understand the problem, we can kind of imagine, this is where we imagine stuff out here, our imaginary space. We'll just kind of continue these vortices. Now we're going to have vortices of sort of equal and opposite sign of their pair. So here I have the clockwise vortex, which is the image of this guy. And here I'm going to have the counterclockwise vortex, which is the image of this guy. And so just like in the real space over here, this imaginary vortex is going to push on this one. This imaginary vortex is going to push on that one, and they're going to run towards the wall. So at some later time, our vortices are going to be close to the wall. So there's our 4 vortices, our 2 ones that are in our actual fluid, and our 2 sort of image vortices, which are just the reflection to allow there to be no flow or sort of have symmetry across our wall here. Now we can see as these things get closer that this guy here is inducing a flow field, which is going to push on that one upward. This one is inducing a flow field, which is pushing on that one upward. This one is inducing a flow field, which is pushing on that one downward. And this has got a flow field, which is pushing on that one downward. So in addition to the fact that still at this point, these are still wanting to propagate themselves into the wall, as they get closer and closer to the wall, then the interaction with its image becomes stronger and it starts pushing downward. So the path that you'll observe these vortices to take then sort of approach the wall and then spread outward. And once they've separated, this pair here will sort of continue to propagate itself along the length of the wall. So they'll just run parallel to the wall. So this one, which is our clockwise vortex spinning this way, and its image, which is the counterclockwise vortex spinning this way, will continue to propagate themselves along the wall. And again, you can do this in the cafeteria by just creating 2 vortices in your cup, and you'll notice them push each other to the wall and then separate and go off their separate ways. Let's consider another interaction that we can set up a simple experiment to see. So again, I'm going to have a red counterclockwise vortex. And this is going to be followed by an identical pair. So this pair will want to propagate itself along a straight line. This pair will want to propagate itself along a straight line. So if they were really far apart from each other, they would just sort of propagate along straight lines as before. But if they're close to each other, they'll start to interact with each other. So we can see that this one's swirling in this direction, the red one. It's going to push on our blue one. It's going to push the pink one down. And it will also push a little bit on that one, but let's not worry about it because it's kind of the furthest away. So the dominant thing is going to push this one this direction and this one down. Our pink one here is going to push the green one, its pair, in this direction, but it's also going to push on the red one and push it upwards. Likewise, when we consider these 2 at the bottom, this one, the blue, is going to induce a velocity on the red in that direction, so that's the propagation of that pair, but it's also going to push the green one inward. And the green one is going to push the blue one outward. So that's where things are initially at time is equal to 0. At some later time, what that means is that this one is moved up there. So now the vortices have moved like that. So the interaction at this time is going to be the same, except now the red one is going to push less strongly on the blue one because they're further apart. So these are going to propagate a little bit slower than they did before. And this pair is going to propagate more strongly because they're closer together. So the green one will push on the pink one hard, pink one will push on the green one hard, and as this continues, this will still want to push these closer together. The blue is going to want to push those together. So this is like all sort of positive feedback, right? So this pair will spread apart, this pair will squish together, and as the squished together pair becomes faster and faster, it will zip through and pass right through the middle of the other pair. And so what will happen then is this pair will have zipped through. Now if we think about the velocities that these are going to start inducing on each other, the red one we'll start lifting the pink one. The blue one spinning in this direction, the clockwise direction. We'll start pushing on that one. The green one, which is also spinning clockwise, we'll push back on this one. We already did the red one. The pink one swirling in this direction, we'll push on that one. And so even later what will happen is the back pair will pass through the front pair, zip through, and then they'll reorient themselves and get themselves back to the original configuration, only they'll be swapped. So at some even later time, we're going to have the same configuration we had initially, but our red one's going to be in the back. Pink one is going to be in the front. Oops, the blue one's going to be in the back. And ignore my colors, I got too excited there. The green one will be in the front. Now we're back to the original configuration, and we can see that the same thing will happen over and over. So these vortex pairs will continue to sort of pass through each other. Now a place that you can actually observe this is with smoke rings. So if we imagine a smoke ring, which looks like a donut. I don't draw so well, so I'm not sure how my donut will look that great. But if we imagine a smoke ring, which is sort of swirling around, and we imagine they're sort of taking a slice through that, an axisymmetric slice, that in cross-section that will look like these point vortices. And so in fact, if you get on YouTube and you just look for videos of smoke rings leapfrogging each other, you can see lots of videos where people do this, where they'll blow smoke rings one after another, and you'll see this kind of leapfrogging phenomena which will happen, which is pretty awesome. So I'd suggest you check that out. So now let's just discuss a few things in 3D. So in 3D, our equation is such, and I won't derive these, I'll just state them, but there's sort of three vortex laws which are given by Helmholtz. And this is again in the assumption of no viscosity and constant density. So these three laws can be summarized as saying that a fluid particle free of vorticity will remain so. Vortex lines move with the fluid, and a vortex tube, which has a strength, is constant. So a vortex tube, an example where you see that is when you look up in the sky on a clear day, and we see an airplane. Behind this airplane, you'll often see two long contrails, which are coming essentially off the wings. And these are very intense vortices which are swirling around. So a vortex tube would be like this collection of vortex lines which are swirling in this direction. So these things can be very intense and can stretch essentially across the distance of the sky. Now one of the cool things is if you ever look at these carefully, remember that always the divergence of the vorticity is equal to 0. So what that means is that a vortex line just can't simply terminate in the flow. So if we look at this airplane and we zoom out and we look across the sky, what you often see, if you look closely enough, so here's our airplane. These will stretch quite clearly for some distance. Then you'll notice some waviness starting to develop. So it turns out these vortex lines are unstable. And then what you'll notice is at some point they pinch off and they reconnect and form a series of essentially smoke rings. And so these vortex lines, when they pinch off, they can't just sort of terminate in the fluid and have just some random sort of vortex lines. They have to close off because the vorticity is divergence free. So on a clear day when there's not a lot of wind or atmospheric turbulence, you can actually see this phenomena quite clearly. And as a final note, let's talk about what this term can represent. So I won't prove this in any detail, but just sort of tell you two effects which this term can represent that can increase or decrease the vorticity of a fluid particle, right? Because this is the fluid particle's vorticity. Its material derivative in time can go up or down according to this term. So two things that can change the vorticity is one is tilting. If I could spell, that would look better. So if we imagine we have a tube, so here's a vortex tube, and it's spinning around, so this whole thing is swirling. If I have a flow which wants to come in and shear this thing and sort of tilt this vortex tube over, we imagine that something must happen, because you've seen this experiment probably in intro physics where someone takes a wheel and they sort of spin the wheel and then they rotate it, and then you feel a force, and then you want to spin, like often a demonstration would be someone sitting in a chair. So they're spinning a wheel in one direction, they turn the bicycle wheel on its side, and then the chair starts spinning. So this is the effect that shows up in tilting a vortex line. The other effect that can show up is stretching. So imagine I had a little vortex tube here sort of swirling around, and it's kind of short and squat. And then I have a flow which comes along and stretches this thing. Now this thing is tall and skinny. We sort of know from experience, if you've ever seen ice skaters, that when an ice skater is spinning and they pull their arms and legs in tightly, they start spinning faster. And so that's sort of the same effect. If this tube gets stretched out, it's going to start spinning faster. So these are sort of two effects that you can see in 3 dimensions where the vorticity can change because of either tilting or stretching. Another place you see the stretching phenomena is in a bathtub. So here's the drain, here's the water, and we start draining the bathtub. You'll notice you'll start forming a vortex here, and then when that thing gets stretched and pulled down the pipe, it gets stretched, and then it becomes very intense. So that's why the thing spins very strongly as it gets pulled and stretched down the drain.